Hello everyone, today we learn about chapter 4 Field Effect Transistor FET Part 2. So the course outline here is we learn about the JFET biasing circuit, which is a fixed biasing, self-biasing and voltage divider biasing. So the fixed biasing is the simplest of biasing arrangement for the n-channel JFET can be solved as a directly using either a mathematical or graphical approach. We can see that the n-channel, the arrow direction toward the source. So we have a drain, we have a gate, we have a source. So this is a fixed biasing, this is the simplest circuit for the JFET. So the resistor Rg here is represented to ensure that Vin appears at the input to the FET amplifier for AC analysis. So for DC analysis, Ig approach to 0 ampere. So if Ig equal to or approach to 0 ampere, so Vg equal to IgRg. So equal to 0 times Rg, so Vg equal to 0 volt. What is a Vg? Vg is a volt at the gate. So the 0 volt drop across the Rg permits replacing Rg by a short circuit equivalent as appear in network below. So that if Vg equal to 0 volt, so we can simplify the circuit like this. So the VGG, so the VGG can connect to the gate and also RD can connect to the drain and source connect to the earth. So this is a simplification if we analyze using the DC analysis. So by using the mathematical approach, so first take note the negative terminal of the battery is connected directly to the positive of VGS. VGS, what is the VGS? VGS is a voltage from gate to source. So we see the terminal first, the polarity. So where is the negative polarity located and where is the positive polarity located? So for VGS, negative polarity located at the source and the positive polarity located at the gate. So by applying Kirchhoff law in the clockwise direction, so we use the clockwise Kirchhoff law, we use the clockwise direction. So negative VGG minus VGS equal to 0. So VGS equal to negative VGG. Since VGG is a fixed DC supply, the voltage VGS is fixed in magnitude, so we can resulting in the designation of fixed biasing configuration. So from this, when we derive the drain current ID is now controlled by Shockley's equation. So current ID drain equal to IDSS time with the bracket 1 minus VGS divided by voltage pinch off bracket to the power of 2. So we know that how to find the ID, we need to use the mathematical equation, which is the Shockley's equation. Then we can use the Kirchhoff current law. So then the drain to source voltage VDS of the output section can be determined by applying the Kirchhoff voltage law S. So we can use the Kirchhoff voltage law or Kirchhoff current law. So if we use the Kirchhoff voltage law, we use the loop. So VDD minus with IDRD minus with the VDS. So VDD, positive VDD minus with negative IDRD minus with the negative VDS equal to 0. So VDS equal to VDD minus IDRD. So since no resistor on source, so Vs equal to 0 volt. So we can say that Vs equal to IR, but no resistor, R equal to 0. So Vs equal to 0 volts. So that if Vs equal to 0 volts, so VDS equal to VD minus Vs. So VDS equal to VD minus 0. So from this, we can find that VD equal to VDS. So when VD equal to VDS, so it's easy. So we can find that VDS value equal to VD. So same with the VGS. So VGS equal to VG minus VS. VGS equal to VG minus VS. So VS equal to 0. Because why VS equal to 0? Because no resistor. So VGS equal to VG. Eh? So no, if no resistor, the automatic is a Vs equal to 0. Plotting Shockley's equation, graphical approach. So we have this diagram. We simplify the diagram. So we can see that. So from the Shockley equation, IDSS is the maximum. So we can see this curve, and the curve go to the BP over 2 and end up with the BP at the x-axis. So x-axis is a VGS and y-axis is a current. This is the ID current. IDSS is a constant. So when VP over 2 so equal to IDSS over 4. This Shockley equation is purpose to draw the curve, especially in the lab. So you get some data and you plot using the Shockley equation to get the plotting graph. So how to find the line, draw line? So from this IDSS, and we know that we have a BP, so we can find the IDQ or Q point for the solution, which is Q point is the point, which is y point is IDQ and x point is a VGSQ equal to negative VGG. When you get the VGG, negative VGG equal to VSQ. You can find the Q point solution. Let's see the example. Determine the following for the given network. So the question asks for find VGSQ, IDQ, VDS, VS, VG, and VD. So the given is IDS equal 10 milliampere and BP equal to negative 8 volt. So how to find VGSQ? So from the formula, VGSQ equal to negative VGG equal to negative 2. So where is a VGG? So VG is a given 2 volts. So VGSQ equal to negative VGG equal to negative 2 volts. So from the mathematical equation, ID equal to IDSS time with a bracket 1 minus VGS over V2 bracket to the power of 2. It's a given is IDSS is 10 milliampere, VGS is a negative 2, and V pinch off is a negative 8, so equal to 5.625 milliampere. So by using voltage Kirchhoff law, so VDS equal to VDD minus IDRD. VDS equal to VDD minus IDRD. So the circuit, this circuit you need to simplify. So the capacitor need to be a open circuit C1 and C2. So you can dapat VDS. So how about VS? VS equal to 0 volt. Why we call 0 volt? Because a VS is no resistor. So if you see the no resistor, automatically Vs equal to 0 volts. So Vg, what is a Vg? Vg equal to Vgs equal to negative 12 volts, and Vd equal to Vds equal to 4.75 volts. The self-biasing is the most common type of biasing method for JFET. Previously, we learned about fixed biasing. Now we learn about self-biasing. So we can see that if self-biasing, so N channel and P channel, at the gate you have a RG resistance at the gate, and source you have a resistance at the source. Previously, with a fixed biasing, no resistor at the source. So self-bias is the most common type of biasing method for JFET. So notice there is no voltage applied to the gate. So self-biasing, no voltage applied to the gate. Vg equal to 0 volts. The voltage to ground from here will always be 0 volts. However, the voltage from gate to source will be positive N channel and negative for P channel, keeping the junction reverse bias. The voltage can be determined by the formulas below. ID equal to IS for all JFET circuits. ID equal to IS for all JFET circuit. ID equal to IS. So the VGS equal to IDRS, okay? Because VGS at the P channel is a negative and VGS at the N channel is positive. Why? Because the current go to the source, but the P channel, the current is out to the from the source. So self-biasing, so eliminate the need for two DC supply. So how to simplify? So you eliminate the capacitor here as an open circuit. So the controlling gate to source voltage now determined by the voltage across of Rs introduced in the source leg of the configuration. If fixed bias is no resistance at the source, but self bias has a resistor at the source. So the current through Rs is the source current Is, but Is equal to I drain ID because at the same same channel, same direction is Is equal to ID, and VRS equal to ID times Rs. So for the indicated closed loop, we find that negative VGS equal to VRS. So when Vg is 0, so Rg equal to 0. So for the self-biasing, no resistance at the gate. So only resistor at the source. So and VGS equal to negative IDRS, VDD equal to IDRD, VDS minus IDRS equal to 0. So the VDS equal to VDD minus ID, RD tambah RS, RP plus RS. So VS we can find with the IDRS. VG equal to 0 volt. Why Vg equals 0 volt? Because the resistance is a 0. So VDS equal to VD minus Vs, and VD equal to VDS plus Vs. So from the question here is that VGS off and IDSS. So IDS is the maximum and VGS off is a minimum for the x-axis, and IDSS is a maximum for the y-axis. So determine the following for the given network. So BGSQ, IDQ, BDS, BS, VG, VD. So from this, we know that VG equal to 0 volt. So automatically RG can be 0 volt. But here is RG has a number here. So how to solve it? So determine the following for the given network. So we need to find the VGSQ, IDQ, BDS, BS, VG, VD. So IDSS equal to 8 milliampere and VP equal to negative 6 volts. So how to solve it? So the solution, the gate to the source, G to the source equal to VGS VGS equal to negative IDRS. Choosing ID equal to 4 milliampere. So VGS equal to negative milliampere times 1K equal to negative 4 volts. Since no VGG, so VGG is no VGG, so we can use this formula ID equal to IDSS over 2. VGS equal to negative IDRS equal to negative IDSS RS divided by 2. So the step by configuration, we can use this formula. So IDSS, so IDSS over 2 and the VGS equal to negative IDSS RS over 2. So we can find the Q point here. So the Q point here you can is between for y point is the IDQ and x point is VGSQ. So you can find the Q point to find the solution. So VDH equal to VDD minus IDRS plus RD. So Vs equal to IDRS, Vg equal to 0 volt because VGG is a 0 volt. So Vd equal to VDS plus Vs. Okay. So the last part of the JFET is a voltage divider biasing. So voltage divider bias can also be used to bias a JFET. So R1 and R2 are used to keep the gate source junction in reverse bias. Operation is no different from a self bias. Determining ID VGS for a JFET voltage divider circuit with VD given can be calculated with a formula. So for the voltage divider biasing, you can use the formula ID equal to VDD equal to VD by RD divided by RD. So Vs equal to RDRS. So the Vg is R2, R1 plus R2 times VDD. This is a voltage divider formula. And VGS, where is a VGS equal to Vg minus Vs. In using the transfer characteristic curve to determine the approximate Q point, we must establish the 2 points for the load line. The first point is ID equal to 0. So we need to find the ID equal to 0 and VGS equal to VG and ID equal to 0. So VGS and ID must be VGS equal to VG and ID must be equal to 0. Then we can find that VGS equal to VG equal to R2 divided R1 plus R2 times is a VDD. So the second point is ID when VGS is 0. Look like this graph. So the example of JFET voltage divider bias configuration. So it's the same with the step bias and fixed bias. We need to find the VGSQ, IDQ, VD, VS, VDS, VDG. So the difference here is that the formula actually, because the voltage divider bias needs to use the formula voltage divider and self bias VG equal to 0, and for the fixed bias Vs equal to 0. So for the transfer characteristic, we use like this. If ID equal to IDSS over 4, so our 8 milliampere divided by 4 equal to 2 milliampere, then VGS equal to VP divided by 2, we can get the negative 2 volt. So the resulting curve representing Shockley's equation. So voltage divider, we use the Shockley equation. It appears as in the figure below. So untuk self bias, we not use the Shockley equation because they have their own equation, but for the voltage divider we use the Shockley equation. So we use the voltage divider formula, and for the how to find ID we need to use the Shockley equation actually. IDSS over 4 and VGS equal to VP over 2 to find the ID and VGS. So we can solve the equation, voltage divider equation like this. So determining the Q point for network. So we know that when ID equal to 0 milliampere, when ID equals 0 milliampere, so VGS equal to 0 volts, like this. ID is 0 milliampere and VGS is 0 volt. So ID, sorry, when ID equal to 0 milliampere, so the VGS equal to plus 1.82 volts. So when ID is 0, so VGS 1.82 volt, like here. When the VGS equal to 0 volt, VGS equal to 0 volt, so ID equal to 1.21 milliampere. So you can plot here. You can plot VG first and then plot ID. The resulting bias line as appear in figure Q point. So IDQ, we draw the line until intersect with the curve. So we can find that IDQ equal to 2.4 milliampere and VGSQ equal to negative 1.8 volts. First, to find by using the graph, find ID, you plot the curve and then you find the VGS first point of VGS and second is a point of the ID. Then you line the graph until intersect with the curve. So you can find the Q point here. So from this, you can find the VD, VS, VDS, and VDG like this. Using the voltage Kirchhoff law, voltage divider, find the answer. So VD equal to VDD minus IDRD, VS equal to VIDRS, VDS equal to VDDID, RD plus RS, and VDG equal to VD minus VG. For the summary, the JFET are unipolar devices. Okay, JFET have a three-terminal source, gate, and drain. So JFET have a high input resistance since the gate source junction is a reverse bias. IDSS for all FETs is the maximum amount of the current flow in the drain circuit when VGS is 0 volt. All FETs must be biased proper operation. Midpoint is most common for use in amplifiers. Unwanted capacitance associated with FET can deal with by using dual gate type FET. So the capacitance can be a source open circuit. So we no need to analyze for the capacitance. Thank you very much.